Today we're going to talk about the use of the 2 by 2 contingency table, especially for its use with inductive reasoning, forming a table of probabilities useful in cross-tabulation of observed or expected data. So let's talk about what we're really doing here is we're looking at two different variables. And we're going to show the relationship between those variables. The relationship as measured when each variable is actually a binary nominal scale. So that we have these two variables, x and y, and each particular case can be classified as having predicate x or not having predicate x, as well as having predicate y or not having predicate y. This is what our 2 by 2 contingency table is going to look like. We're going to have the rows indicate x and not x, and we're going to have our columns indicate y or not y. The resulting four cells, A, B, C, and D, will represent the different possible interactions between variables x and y. Cell A will be those cases where both x and y are present. Cell D will be where neither x nor y is present. Let's now observe 12 different cases, each one represented by a different coin. So suppose we observe our first case having characteristics x and y. We observe another case with that situation. Then we observe a case that has neither, and another case with neither, and another case. And we observe another case over here, a case over here, and so forth. And we end up then with our individual observations being noted. The observed count into the four cells is what we're going to record. Then we're going to add across and down to get our marginal totals and our total sample size. We can then calculate probabilities, and that's very simple. Any probability is simply the part divided by the whole. So in order to calculate the probability of winding up in one of our four cells, we would just look at that particular observed quantity and divide it by the total number of cases that we happen to be considering. So let's suppose that we then record our number of observed cases. 3 cases in cell A, 0 in B, 3 in cell C, and 6 in cell D. This means that we had a total of 3 cases where x was present and a total of 9 cases where x was absent. We had a total of 6 cases where y was present and a total of 6 where y was absent. In other words, we have 12 total cases, and they are distributed in the 4 cells in this way. In order to get the probability of any particular case being in any particular cell, we take our observed frequency in that cell and then divide it by the total number. So we have 3 divided by 12, or 0.25 of our total in cell A. We did that for each of the 4 cells. Now notice that if we add all 4 cells' probability together, we're always going to equal 1. And if we add all 4 cells' frequencies together, we're going to get our sample size. A conjoint probability is really the probability of a conjunction of both x and y. And in this particular case, all we'd have to do to get that is we'd look at the quantity in cell A divided by our sample size. And look, we've already done that. The joint probability of x and y occurring is 0.25. Then let's take a look at how we would get some other probabilities, such as the disjunction, x or y or both occurring simultaneously. Here we could add the three cells A and B and C and then divide by our total sample size, or we could do 1 minus the probability in cell D. In this particular case, we could add these three numbers and get 0.5, or simply take 1 minus 0.5, and we see that the probability for the disjunction in this case is 0.5. Another kind of probability that we should talk about is a conditional probability. And that means, what is the probability given that we already know which row we're on or which column we are on? In other words, if we already know that x does exist, what's the probability of y? Or if we already know that y does exist, what's the probability of x? And so we can actually calculate the probability of x given y, or the probability of y given x. That's what we mean by conditional probabilities. Now, so far we've just dealt with observed frequencies. Sometimes the construction of these tables utilizes expected frequencies. And what that does is it assumes what we call statistical independence. If you're going to be good scientists, if you can possibly make those observations and put the observed frequencies down there, that's the better way of doing it. There are actual statistical tests like the chi-square test that allow you to compare the observed frequencies to the expected frequencies.